Okay, so let's start our evening session. The first speaker is Kargaltsev of George Washington University, and he will be talking about X-ray, pulsar with nebulae, and not only X-ray. So Oleg, please go ahead.
Thank you, George, and thank you for invitation to the organizers, because I'm taking part in this conference for the third time, and it's always a great pleasure to be here. So I will be talking about the pulsar wind nebulae, and I will focus on reviewing recent developments in this area, and I will primarily restrict myself to the X-ray observations and a little bit, maybe I'll show a little bit of radio images. Simply because of the limited time, I will not be able to talk about the developments at very high energies, such as TeV and GeV. So there's been quite interesting developments there as well. I'm not going to be able to cover them. So a lot of new results and recent work that I will be showing is done in collaboration with these people, and this is really quite incomplete list here, right? So let me start a little bit with a historical introduction. So these are images of pulsar wind nebulae, which are really brightest pulsar wind nebulae, which were obtained with ROSAT, right? So maybe you still can recognize, if you saw just Chandra images, maybe you still can recognize which pulsar wind nebulae are these. So this is a Vela, Crab, and MSH 1552. I will, of course, show the Chandra images as well. So even with these sort of data, the basic properties can be actually evaluated, and the basic physics can be put in place. So there is this picture that's been out there for a while, and it hasn't changed a lot. I mean, the details have changed, and many physics has been added into this picture, but sort of at large, it still remains more or less valid. So I just took the picture from the Haranyan, but of course it's actually based on the earlier works, in particular the important work by Canonical and Canonical. So what's shown here is there is a neutron star, right? So this magnetized sphere that produces particles and large amplitude electromagnetic wave, right? So this wind of particles is initially, we will call it like unshocked wind, right? It goes through the termination shock because it needs to slow down. Initially, it's highly relativistic flow with Lorentz factor of maybe a few hundred. So it goes through the termination shock, after which there is another region which is actually the visible nebula. That's what we really refer to as a pulsar wind nebula, the synchrotron nebula over here, where the motion of particles becomes randomized, and as recent 3D simulations show, the magnetic field possibly becomes somewhat turbulent as well. Then there is another boundary over here, which is really a forward shock. In that sense, this shock front can be called as a reverse shock, or more often it's called a termination shock. And somewhere there is a forward shock where there is an interface with the ambient interstellar medium or ejecta in the supernova remnant, if this pulsar wind nebula is young enough, right? So those are basic zones, and downstream of the shock, of this termination shock, we have a really magnetized plasma, and we have highly relativistic particles in this plasma. So you'd expect at least these two important emission processes happening, the synchrotron and inverse Compton. I will primarily in this talk focus on this process. So once we know the emission process, the quite simple estimates, but useful ones, can be made. So for instance, if I parameterize these equations using magnetic field in this region and the Lorentz factor of the particles, I can write down the energy of the synchrotron photon. I can actually write down the energy of inverse Compton photon as well, through the energy of synchrotron photon eliminating gamma, for instance. But I'm not going to need this equation in my talk today. And then one can actually estimate the characteristic size of this wind bubble by a very simple argument by saying that the pressure of this relativistic wind, which is really given by E dot, by spin down rate of the pulsar, should be equal to the ambient pressure, whatever it is inside the supernova remnant or somewhere outside there. If you plug in reasonable numbers, so this is a young pulsar, this is sort of typical pressure inside maybe supernova remnant, which is a few kiloyears old, then the size, the expected size, is a fraction of a parsec for this bubble. It's really an order of magnitude estimate. It can be a factor of a few different, right? So then one can estimate the synchrotron cooling time, how long these bubbles of synchrotron emission that we see in X-rays. That's why we actually change parameterization from gamma Lorentz factor to energy of an X-ray photon. How long they will live, how long can we expect to see them, and that's going to be on the order of kiloyears. Right, and it's again very much order of magnitude estimate. So one typically parameterizes the luminosity of the observed pulsar wind nebulae, introducing this efficiency, radiative efficiency, that is just a coefficient between E dot and the actual observed luminosity. So there is surprisingly very large range of these efficiencies based on current observations of pulsar wind nebulae from 10 to the minus 5 to 10 to the minus 1. Right, this is another picture which is more recent. I stole it from the website called Astrobytes. Someone drawn a picture of a pulsar wind nebula with a little bit more detail than Aharonyan did, which includes some interesting things like a collimation by the hoop stress of the jet and the backflow from the termination shock and so on. That's from recent MHD simulations. It also includes something that hasn't been shown, is that this interface and the forward shock. Yeah, really there's more detail there than I'm actually going to be able even to discuss, but I'll refer to some of these things that you saw in those pictures later in the talk. So there was this a big step forward in terms of studies of pulsar wind nebulae, which came with the launch of Chandra and XMM-Newton. So, of course, everyone by now knows what are actually these observatories, what range of energies they're observing, and how great is the resolution, really comparable to the resolution of optical telescopes, 0.5 arcseconds for Chandra. For XMM, it's not, maybe so good, but it has much larger collecting area, a larger field of view, but also the other disadvantage is a higher background. So, both, of course, observatories are useful, but Chandra is particularly useful for compact pulsar wind nebulae or faint, very faint pulsar wind nebulae. So by now, if you count all these little tiny faint pulsar wind nebulae, probably around 100 pulsar wind nebulae have been detected in X-rays, right? And then more recently, there is also a hard X-ray telescope, NuSTAR, that has also poor resolution, worse than XMM, but it goes to higher energies. Right, so I will primarily focus on what we have learned with Chandra in this talk for the reasons I explained. In particular, the things that were actually enabled by Chandra and XMM, the ones that are relevant for pulsar wind nebula science, is the high-resolution images which actually reveal the fine structure of pulsar wind nebulae, and I will explain in my talk why this fine structure is important, why it's not just some kind of incremental details, and the Rosat images would be sufficient. It's not. There is a lot of interesting physics hidden in this fine geometry there. Then with Chandra, it's possible to do spatially resolved spectroscopy with ACES. That means we can actually study how the particle distribution evolves with the distance from the pulsar in different directions. That's also important because winds are anisotropic, right? Then what's possible with Chandra is actually resolving very faint sources. And that helps in, let's say, I give one example. It helps when you say looking for a potential explanation of the TeV source and you're finding some resolved source and you are able to actually classify it as a pulsar wind nebula. That's only possible with Chandra. So there's sometimes subarcsecond localizations allow to discover compact objects that turn out to be pulsars. I'll give an example later through multi-wavelength observations, right? So localizations are very important, subarcsecond localizations. And also being able to disentangle different spectral contributions, for instance, thermal emission from supernova remnant, from non-thermal, from the pulsar wind nebulae, is really can be done with Chandra very well and with XMM to some extent, but it was already mentioned by Pat and Samar. Right? The other demonstration of how much progress was made with the launch of Chandra and XMM is possibly this graph of articles that are written on pulsar wind nebulae as a function of time. And that is about the time when the Chandra and XMM were launched, right? So there is a big growth there. So again, just remind you how the pulsar wind nebulae looked like before, and that's how they look after with the Chandra. So we recognize some famous ones. The ones from the previous slide, the Crab and the Vela pulsar wind nebula are here, right? Then this is the other one shown before. So this is just a gallery. It's not incomplete actually, and there are all kinds of shapes you can see here. And rather than just being a zoo, it's actually there is a very important information encoded here, and I'll try to explain how this information can be used later in my talk. Right. So basically, this information is encoded in the shapes and the orientations of pulsar wind nebulae. So you can see that many of them have toroidal and polar components, which are sometimes called just toroid, jets, or rings, whatever. So that carries information about orientation of pulsar spin axis with respect to the observer's line of sight. And then I also believe that there is an information here that is encoded about the angle between magnetic and spin axis. So I'll talk about it a little later in detail. The other important factor which affects the appearance of the pulsar wind nebulae is the properties of the ambient medium, right? What's the pressure, for instance, of the ambient medium? Is it uniform medium or non-uniform medium? Is there reverse shock or not? And actually, the last important factor that I would like to mention is the Mach number that corresponds to the ratio of the pulsar velocity to the sound speed in the ambient medium. Now, this Mach number can be also relevant in the case when you have a reverse shock coming and pushing on a pulsar wind nebula. Then it might be defined slightly differently. Right, so this is a demonstration of what happens when you have a low Mach number, like of less than 1, so subsonic motion, and the supersonic motion. This is a high Mach number. Of course, these are, they are not, these schematic pictures, they are not resembling the complex anisotropic pictures that you can see here. It's just like to demonstrate only one thing, is that the Mach number, large Mach number and supersonic motion distorts the pulsar wind nebula substantially. There's still those regions that you can still recognize in this picture, the unshocked wind with indetermination shock, the shocked pulsar wind, the contact discontinuity shock, ISM, etc. So the regions are still there, but the shape is distorted. Now, if we put a really realistic anisotropic wind, this picture should become more complex, of course, right? So let's recall that the typical pulsar speed, just based on the measurements, is of the order of a few kilometers per second. And of course, there is a distribution there. Now, the typical speed of sound in the ISM can be estimated like this. This is a warm ISM phase, so it's about, let's say, 10 kilometers per second. So you can see that subsonic motion is really only possible for pulsars that are still in their host supernova remnants, right? So the younger ones, or the ones that were not kicked so much during the supernova explosion. If you wait long enough, or if the pulsar is kicked fast, it will be moving in the normal ISM, and it has to be supersonic motion, therefore, right? So let's consider first the case of more or less isotropic pulsar wind nebula in supernova. There we can use this estimate to estimate the size, right? And that gives that 0.2 parsec that was shown before. And the this is an okay estimate for that case when you have a pulsar in the supernova remnant. You can still use similar kind of estimate by quanting pressures for supersonic case, but there you have to add the pressure, the RAM pressure to the ambient pressure, and it will become dominant there, right? Just to show some more images, actually zoomed in images of the pulsar wind nebula that actually have been studied in detail. So they are kind of collected in this slide and in the next slide. What does it mean? It means there was a dedicated long Chandra observation, or the pulsar wind nebula is so bright, well, like in case of the crab, that maybe you don't even need long Chandra observation, but it's either of those two. So we have good data on most of these nebulae. Well, there is some improvements maybe needed for a couple of those, but we have a pretty good data for these ones. And that's why I will focus next on these nebulae. So these were the pictures, and that's the same well-studied pulsar wind nebulae collected in a table. There's about 18 objects, I believe, here, right? And the details, the exposures, and the total fluxes are here. So, of course, the first one is crab, right? There's a lot has been said already about the crab, so I'll go very quickly. This one is a torus jet type pulsar wind nebula. It's obviously not supersonic with respect to the environment of supernova remnant. So remember those words because they will be important. The ring, the inner ring, right? The torus and the jets. The spin axis coincide in this case with the velocity vector because it was measured how it's moving. And the inclination angle, I will explain what's this zeta angle a little later, but this actually it is the angle between the line of sight and the spin axis of the neutron star. So that's this zeta angle, so it's 60. It's possible to measure this angle because you have this ring that appears as an ellipse, and it is becoming ellipse due to the simply projection effect. So we assume that it is actually a ring. So then you can get this angle, right? So it's interesting to study this structure. There's lots of detail. So let's just mention the jets. So according to most recent simulations, the jets are actually formed by the backflow from the equatorial outflow towards the pulsar, where there is a hoop stress that actually forms the jet, and those are the references, right? So, but if you look at the torus is really complex. It has all this fine structure, which is called wisps. So those are motions in the torus that you can clearly see here. These are not the only motions in the pulsar wind nebula, because it happens that on somewhat larger time scale, this jet is also kind of wiggling. It's actually the motion of this jet is sort of consistent with a rotating helix and the time scale of a few year time scale. So you can look at the Weisskopf papers, right? So this is another pictures of the crab, which are interesting. So this is somewhat perhaps better demonstration of the wisps. It's of the wisps moving in X-rays. So this is X-ray observations, right? And so this is multi-wavelength image of the crab at the done with JVLA, Hubble, and Chandra. So what's interesting in this multi-wavelength image? Well, first of all, you can kind of see three jets, really, if you look at it, different colors, different wavelengths. So it's kind of odd to have three jets in a pulsar. One could be part of the filament that goes like that, but the other two are actually not sure how to explain too. Then if you look at the multi-wavelength image, what one can find is that these wisps, they do not coincide in contemporaneous observations at different wavelengths. At different wavelengths, they're slightly different places. And that is still, I think, remains to be established. Why? Thankfully, we can actually track these wisps very good, and thanks to HST. This is not the YouTube movie. That's the movie that I made from the HST ACS images that were obtained during a later campaign than that movie. So here you can see that some of the wisps are not moving. You can actually measure how they slow down with the distance from the pulsar. The velocity field possibly can be reconstructed here, but that's a topic of another talk, right? So there is also a lot of information still in the archival data, if you like, because there's this filter that avoids bright filaments, and there you can see the counter jet of the Crab pulsar better. We have recently obtained also ALMA images of the Crab nebula. They're not very good because it was done during the very early phase. But anyway, you can see still the torus, this wisp region at the 100 gigahertz very well. And you can see one of the two jets and what I think is a filament, but not the third jet. Let's go through a little bit of observational review on the other very interesting nebula, which is Vela Nebula. So this is a little older pulsar, also in the supernova remnant. So if a Mach number is larger than 1, it's not by much. It's probably of the order of 1. There is an analogy to Crab because it does have some kind of equatorial component and it has polar outflows. Although equatorial component looks quite different here. It's a kind of double ring structure. So it's different from Crab, where all these rings and wisps, they kind of seem to be in the same plane. Here you have two planes, maybe one below and one above the truly equatorial plane. So why is that? Possibly it's related to a different magnetic inclination angle. So the angle between spin axis and magnetic dipole axis, that would be the simplest probably explanation put forward by Helfand yet. What else is here different from the Crab is that the Vela really kind of features inner and outer jets. So in the Crab, you can't really make this division. It's jet, single jet becoming fainter as you go along the jet. So here, what we call inner jets, they are much brighter than the outer jet, in particular this jet. And then there is some interesting asymmetry, is that this inner jet is brighter than this one, but this outer jet is brighter than the other one, right? So that's maybe implies that there is some bending in three-dimensional space going on as you go further away from the pulsar. And some of this bending we can actually see in the movies that I will show soon. Then there is this interesting structures at the base of the jet, possibly related to this hoop stress collimation of the backflow that I referred previously. So, but it's still unclear why there is such a drastic contrast between inner jets and outer jets. We cannot really see motion, steady motion here in this torus. There are some indications of variability, but not like we can resolve wisps that are moving in the torus, right? So we can't directly perhaps measure this motion, but we can measure motion in those jets, and then I'll show how it looks like. Well, the standard synchrotron brightness estimates can be used to get the estimate of the magnetic field and the electron energies. What's interesting, though, is actually to add radio to this picture. So the radio is blue, the X-ray is now red. There's a complete anti-correlation, if you like, or the complete lack of correlation between X-rays and radio. I'll be just very brief. I think it implies that there are two different populations of particles, two different SEDs there, because there is very similar spectra of these outer jets and this compact nebula. The spectra are very similar. There is absolutely no radio counterparts to these X-ray jets. Rather, the radio emission comes from these lobes. And these lobes are not completely devoid of X-ray emission. Actually, interestingly, there is a harder X-ray emission with harder spectrum that is kind of faint, but it fills this lobe. And there's a very sharp boundary here. So I don't know, one possibility to explain this is that there is this crosswind from here, some motion within the supernova remnant causing another shock here, and there may be additional acceleration going on in this area producing different spectrum. I think it's an interesting possibility discussed in Bykov et al. 2017. Now I promised to show some motions and that the jet is actually, does something, some bending. So it does look really like a rotating helix, if you like, and obviously it has to be three-dimensional, so it is possible that it has a bend toward the observer, but why it is always stays brighter than this outer jet over here, it's not clear. Now, what's the reason for this apparent rotating helix? Well, there can be two really reasons. One is the kink instability that is kind of persists there and behaves in more or less regular way for some time, the time that we observed, or there can be actually a precession of the source of the jet of the neutron star. I'm not going to go in that possibility. So the inner nebula is also variable, but there's no time to quantify those details there. Now I mentioned that the spatially resolved spectroscopy is advantage of Chandra. And here we can really study the structure of the nebula in a spectral map. So this is a photon index, and you can clearly see the very hard inner nebula, the hard jet over here, and then there is this harder region over here, and actually there would be another one there, but not well shown, right? So there is anisotropy, clear anisotropy in how the SED behaves, right, with a distance from the pulsar. So that should be taken into account because very often things are really averaged around this angle. Now, I don't have time to show any other spectral maps, but we have done spectral maps for all these pulsar wind nebulae that are well observed by Chandra, and that allows us to measure the spectral indices in the sort of innermost region close to the termination shock, so hopefully there's no effect of cooling, maybe it's a truly injected spectrum there, right? So if you take it like that, then these numbers may be more interesting, so you can convert photon index into a slope of the electron SED very easily for synchrotron, and so whichever you like, the slope of SED or the photon index, it's either that or that you can look at. You can see in terms of the slope of SED that there are plenty of pulsar wind nebulae with injection indices that are below 2, and I'll leave theorists to comment further on that. Now, is Crab and Vela the only temporally variable, like varying with time nebulae? No. For instance, there's one nebula here that we have started to study a few years ago. We obtained 3 images at different epochs, and there's clear change in the morphology of this nebula. So there's another Chandra observation series actually approved, so that will be more interesting to discuss when we get those. But it's a clear motion of that possibly jet feature. Now, if you actually add all of these observations and you zoom out, there is an interesting extended fainter structure on larger scales here. Why is it interesting? Because it kind of has a sharp boundary here implying some other shock at the larger distance, and then there is interesting extension here. You will see those extensions in supersonically moving pulsar wind nebulae. We call them misaligned outflows. I'm not sure if that one of those, but it's a peculiar thing. Now, if you put it in the multi-wavelengths perspective with the radio together, so we unfortunately do not see any radio from this region. There's plenty of supernova remnants, but the nebula itself is not detected. There's a TeV source here, and it yet to be remains to be understood how these two are related, given that sharp boundary over there. The other nebulae that I think are very interesting, that are emerging from these very deep observations with Chandra, is this one. So this one, if you look with Chandra, you can actually see a very faint ring over here, which allows you to measure the tilt of the spin axis to the line of sight. It's also variable with time, this nebula. And the other recent work found this little jet, which is again looking like a helix. So we don't see how it rotates or precesses, but it is a nice helical jet. Now, as I promised, Chandra can also deliver some very faint nebulae that you otherwise wouldn't find. And there's probably plenty of those still in the archival data. So this is just an example of Chandra observation where we studied this pulsar. So it was designed to observe this pulsar, and next talk by Noel Klingler will address that nebula. However, by accident, we found this extended source over here, right? It's a really tiny, faint, extended source with the central source. And the there's not so many extended sources that you find in X-ray images of that kind with the bright source in the middle. It could be AGN, but there's nothing in the radio or optical. Then we concluded it's a pulsar vein nebula. And then we recently found a paper that is very recent, that there is actually a gamma ray pulsar was just discovered right there. So, I mean, but basically just using Chandra, you can find it and say that it is a pulsar vein nebula. So there is a lot of work to be done still. So the other sort of topic that I would like to talk for 5 minutes perhaps is relating the pulse shapes and pulsar vein nebulae morphologies. You should forgive me, I will be going really quickly through the pulsar light curve terminology, sort of, because of the lack of the time. So I will basically say that there is a rotating vector model everyone probably knows here. There's many angles that can be used there, but two most important angles is the angle between rotation and magnetic axis, or let's call it a magnetic inclination angle, just for shortness, and the other is the viewing angle, right? So those are the two angles between the line of sight and the spin axis. So then there has to be some assumptions made about where the emission comes from the pulsar, from what regions of magnetosphere, before we can compare make sense out of the light curves, right? And so there has been a lot of work done here. I cannot go through this, but the radio emission still probably comes close to the pole, right? Close to the magnetic pole, and it may be a complex region which is like a hollow cone rather than a pencil beam, but there's no time to discuss that. And the gamma ray emission comes from the outer magnetosphere, perhaps close to the light cylinder. So that's all I'm going to say about that. Then there are some conclusions that are kind of robust, maybe even regardless of the exact model of magnetospheric emission, right? So that single radio pulse and weak or no gamma rays imply that the line of sight and magnetic dipole axis are close to rotation axis. If you see strong gamma rays, no radio, maybe you're probably viewing orthogonal rotator at some substantial angle with respect to rotation axis. Orthogonal rotator means alpha is 90 or close to it. And then there's also, one can continue and say that if you see two wide, well-separated peaks in gamma, then this viewing angle is 90. If a single peak, 45, then this angle is 45, and so on. So it's basically, there is dependence also on the alpha angle here, which is not mentioned. So this is more complex than I just described, but these are sort of basic features that can be expected from the light curves. Now, that's how complex it gets. One can produce detailed maps of how the emission looks like with rotation phase and viewing angles. So if your line of sight crosses here, you will see two peaks in gamma rays, one here, the other is here. If it crosses line of sight somewhere there, then you wouldn't see any gamma rays. So people do that. They plot, they try to infer from gamma ray and radio light curves these angles, zeta and alpha, viewing and magnetic inclination angles. That's basic. The color coding is showing how many peaks you have, what's the separation between the peaks. These are different kinds of models produced by different groups. I'm not going to explain that. I just want to say that with the growing sample of those nebulae where you can resolve this fine structure and constrain zeta angle, one can actually constrain better those magnetospheric emission models, right? So, and one can maybe even use the relative strengths of equatorial and polar components in the pulsar vein nebula images to constrain the alpha angle, magnetic inclination angle, right? So for which nebula you can do it? Well, let's say for these ones where you can find these structures such as jets, rings, tori, those things. And so when you start putting things together, I think it's really helps those people which model magnetospheres. It also can go the other way. So sometimes you cannot understand the structure of the nebula, but you have that gamma ray light curve from which you can go the other way and try to predict, explain what you see in the Pulsar wind nebula. So this is just an example of if you make conclusions about these angles from the images of the Pulsar wind nebula and you plot it on top of those pictures produced by light curve modeling community, those are the allowed regions. Now I'm going to kind of quickly scroll through the rest of these examples where you can infer angles from both light curves and Pulsar wind nebula images. I'm just going to demonstrate that these are quite different light curves sometimes. Like in this one, you have a strong jet relative to the torus. The torus is very weak. You don't have a radio pulse, and so in my view, maybe it means that you have relatively small alpha, magnetic inclination angle. Here is clearly you have a very small zeta angle. The torus, it looks like a ring, not ellipse, right? So that may be helpful. What's interesting also is to look if there is any change in the spectrum of the nebula as a function of the alpha angle. The supersonic nebulae I'll leave to the next talk by Noel Klingler. So this he will show the images of the population. He will focus maybe on 4 or 3 objects, but there is like 20 supersonic pulsar wind nebulae which have an extremely interesting, recently discovered misaligned outflows. And in these cases, you can also use the structure of the compact nebula to infer the geometry of the pulsar and magnetosphere and to compare to the light curves. But Noel will talk about it. And in the remaining 2 minutes, George, I will very briefly show an example of the exotic system. So one is binary. In this binary, we just discovered the transient pulsar wind nebula as 2 series of observations. This is B1259, high mass binary. So we continue monitoring this. More observations will happen. Why is it interesting? Because the speed of this clump is like 10% of the speed of light. And it must be moving in a very rarefied medium. Actually has to be a pulsar wind. So this clump, which is probably some material from the decretion disk of the star, is actually launched into a pulsar wind and goes with a pulsar wind flow. I'm not going to go through these estimates. There are a couple more systems that are promising in this respect, and they will be observed soon. And the final slide is another exotic case of the Pulsar or Magnetar wind nebula that was mentioned actually already here, so I don't have to say much. But what I would like to say is that there is no doubt it's a nebula because we see it long after the flash of the Magnetar, so it's not a dust halo. And moreover, it's persistent in the sense that in the very old Chandra observation from 2006, the flux of the nebula is about the same as in this recent XMM observation. So it can persist for very long, and therefore it's a way to find transient or dormant magnetars, perhaps. So finding those faint extended objects in existing Chandra data is important. And here is my conclusions. I'm just going to leave it here because of the lack of time. Thank you. Sorry, George.
Thank you, Oleg. What are the questions? Sergey.
Just about the last slide with the Magnetar and Nebula. Is it clear now if this nebula is powered by rotational energy losses or magnetic energy losses, or both are possible?
I think it has to be powered by magnetic energy. The question that remains there in my view, others can disagree with me, but whether it is actually was produced in some kind of cataclysmic event that we did not register, and it still lives and slowly may be changing, but too slow for us to see how it's changing, or is it sort of a persistent phenomenon that was always there since the birth of that Magnetar that I don't know.
Other questions? Okay, I do not see any, so let's thank the speaker again. And the next speaker